Hello everyone and welcome. In this video, I want to talk to you about autonomous ship systems and cybersecurity, where they overlap and where things can go wrong. My name is Mohammed Arvas. I'm a PhD student at Tallinn University of Technology, Estonia, and my research focuses on research on the cybersecurity challenges in autonomous ship systems. I'm trying to make these videos so people can understand more on the maritime cybersecurity or how far we are close to the autonomy in ships or maritime by a researcher who is currently working on this topic, and hope it really helps you if you're interested about this general topic. So let's get started. Today I want to take you into a space where three worlds meet: maritime operations, artificial intelligence that everyone's talk about, and cybersecurity. We constantly hear big promises about autonomy: ships that navigate themselves, optimize routes, reduce human error, or cut costs. But autonomy also shifts risks. Instead of relying mainly on human judgment, we rely on the sensors, algorithms, data pipelines, and decision-making software. When those systems fails, the ship still acts, but it acts incorrectly. So in this talk, I want to do the three things. First, show what autonomous ship system actually look like, the real architecture, not just marketing slides. Secondly, explain how AI is used, especially in perception and navigation. And third, discuss how cyber threats, particularly adversarial AI, change the risk landscape. As you all know, that autonomy doesn't remove risks. It simply moves risk into the new places, and those places are often misunderstood even by the engineers. So why maritime cybersecurity matter? When we talk about the cybersecurity, many people still imagine laptops, email, and stolen passwords. But ships are far beyond that. A modern vessel is covered with computers, digital controls, and automated systems. Navigation, propulsion, cargo pumps, environmental systems, communication, all really heavily on the software. And here is the crucial difference. When digital systems fail on land, you restart the server basically, yeah? But when digital systems fail at sea, you lose control of something and waiting tens of thousands of tons. So which cyber incidents have already caused navigation confusion, delayed voyages, disabled bridge systems, ransomware, locking entire fleets, ports shutting down, and GNSS spoofing marketing ships believe they are somewhere else. And when something fails at sea, the chain recognition is huge. Collision, grounding, pollution, economic disruption, or safety consequences. So we have to stop thinking cybersecurity is an IT problem. In maritime, cybersecurity is an operational safety problem. So no cybersecurity, there is no safety. So let's break the ships into two digital domains so this becomes much clearer in your head. First, IT, information technology. So this is the administrative side of like email, databases, internet access, crew communication, documentation, planning, and fleet management. Second, operational technology. This is the physical A-word, engines, propulsion controls, or ballast pumps that is actually taking some water into the seawater into the ship. Power management, electronic charts, radar, route control, or cargo systems. Historically, IT and OT were isolated. So today they are connected for reasons like remote diagnostics, fuel efficiency analytics, remote updates, centralized monitoring, or cloud services. Great for efficiency, but terrible for attack surfaces. Because once malware attackers enter IT, they can pivot sideways towards OT. And when OT is compromised, physically movement becomes unsafe. So the real danger is not that someone raised the mail, it's that someone indirectly influences propulsion, steering, or navigation. Imagine that. This is what you will see in a conventional ship. Everything is one place. You will see that radar, automated identification system, electronic charts, weather, cameras, or engine info, all layered into a clean visual picture. For the crew, this reduces workload and improves clarity, so it supports better efficiency of the work. But psychologically, it creates blind trust. If GNSS lies at this displays the wrong position, which is electronic chart. If automated identification system, which is AIS, is falsified, the fake ships appear or real ships vanish. If radar data is manipulated, obstacles disappear. To the human eye, everything still looks correct, but because the system integrates wrong input into one harmonized picture. And that's the exact moment where cyber attacks exploit. They don't need to break everything, they only need to corrupt one critical input. So therefore, in this presentation, we will take our eyes into the future direction and try to understand the autonomous vessels. But what is autonomous vessel? In maritime, we have named them as maritime autonomous surface ships. Before we go deeper, I want to make sure we are all talking about the same thing. When we say MAS, we are referring to the maritime autonomous surface ships. In simple terms, these vessels that can perform part or sometimes most of their navigation and operational functions without constant human control on board. That doesn't automatically mean no humans at all. In many cases, people are still involved, but they may be on shore or supervising or just monitoring or taking control only when it's needed. So MES covers a spectrum from a decision support system that assists the crew to highly automated ships and eventually fully autonomous vessels operating the minimal human intervention. We have, of course, a classification of autonomous vessels. Autonomy doesn't arrive instantly. It evolves like a human evolution. So the level one is what we call the human operate fully and autonomous support decision making, which is now maybe in the airplanes also. You can see that there is some autopilot option that follows the track wherever you go. You decided to go. So level 2 is humans on board, short centers can assist. Level 3, no humans on board, which is a remote operators controls, which is including this kind of a future AR, augmented reality or virtual reality controls. Level 4, fully autonomy, ship decides and acts independently, fully. So within these levels, humans move further away. Systems take more responsibility, the transparency drops, cyber exposure increases. And the key truth is human became monitors, not an operator. And as you may know that human are terrible monitors when automation appears reliable. As you may see how we use the language models in our current life, they stop questioning, especially when nothing looks wrong to us. But before moving on, we have to think about how artificial intelligence is actually working in maritime autonomous surface ship. So, at the heart of the autonomy is a perception, understanding the environment, which we called as situational awareness. All process data from camera, LiDAR, or radar, AIS, GNSS, sonar, or environmental sensors. So the first phase is the situational awareness phase. It detects ships, buoys, coastlines, or whatever the ship has surrounded by. AI does not see the world. It processes pixels, points, vectors, and databases. If attacker manipulate what AI sees, everything downstream collapses. And unlike humans, AI does not feel adopt. It outputs confidently. And as you know that if you try to change the have a talk with the language models nowadays, you will feel that you can easily trick them with some basic command prompts that will lead you to decide that what is wrong is actually you can show them it's correct, uh, which confuses you, but they are still confident about they did a mistake for 2 plus 2 equals to 5. But anyway, if we continue, these situational awareness systems is the main concept, which is LiDAR is a fascinating tool. For example, it fires laser pulses and builds a 3D model of the world, essentially millions of dots. So airplane has also the same things. So the AI turns those dots into recognized shapes, distance, and speeds. Add radar and camera to the mix, and you get the sensor fusion. But this environment is also fragile. Light interference, reflection tricks, projected patterns, adversarial patches, fake signals. I can count many more. If an attacker injects misleading patterns, the AI doesn't reason like we do. It accepts them as truth. Of course, let's slow down the system down and walk step by step. So the sensor collect data, AI interprets realities, decision engine calculates responses, control executes maneuvers, and the risk is not only at the end, but the earlier manipulation occurs, the more dangerous it becomes. If the first step is corrupted, everything after logically follows, but follows something false. This is how attacker works. They don't fight the engine, they fight the brain that tells the engine what to do. The second and maybe the most critical part after the situational awareness is the collision avoidance. So based on the sensor data, the system predicts how other vessels are moving, identifies the potential conflicts, and proposes or executes maneuvers that follow some collision regulations that we had in sea. In other words, AI is helping the ship answer the question, if I continue this way, who will I hit and what should I do instead? Finally, we have the global Optimus planning model. Beyond just avoiding incidents, AI also supports route optimization, looking at fuel efficiency, weather traffic, or safety constraints that to plan the best possible path. What's the important to keep in mind is that all these functions depends heavily on the data, integrity, and reliable communication. If the data is wrong, manipulated, or delayed, AI can make confident but completely wrong decision, and that's why exactly cybersecurity becomes so critical in this context. This feedback loop runs constantly in maritime autonomous systems. It detects what exists, it analyzes what is happening, it plans what should I do, and it execute action. So every loop influences the next one. If the model misdetects an obstacle, the ship plans for a world that doesn't exist, and produce safe-looking but unsafe actions. Now I want to actually show you a real kind of more understanding of the composition of how AI and maritime interacts with them on an architecture phase where we designed this model and published as a paper. So let's take a look at briefly at human autonomous ship actually works as a system. So at the top you will see a ship as a whole layer. Inside that, the first layer is the primary function systems: navigation, communication, propulsion, and steering, and the sensor data analysis units. These are the core technical functions that keep the ship moving and aware of its environment, as we discussed in situational awareness phase. Below that, we moved into decision making and autonomy layer 2. Here's where the algorithms start using the incoming data to understand the situation, evaluate the option, and propose or execute actions. So you also see the elements like feedback loops, integration with vessel traffic management, and machine learning components. All of these help the ship adapt and improve its behavior over time. Then we get into the inputs for decision making. So data is collected, cleaned, fused, and analyzed. From that, the system generates navigation decision, and finally those decisions feed into the collision avoidance systems and other control functions. One important detail: even if highly autonomous ships, there are still human overridable controls. That means that the operators can step in when needed, especially in a complex or unexpected situations. So in short, we can say that the sensors collect data, analyzes turn into awareness, AI generates decision, and control systems execute them, all while humans still remain in the loop. And again, if any part of the chain is compromised, especially data, the entire autonomy stack becomes vulnerable. So this is why I want to take you a very interesting part, especially in this content. So the introduction into the adversarial attacks. Now we understand how the system works, but now what are their cybersecurity issues? The interesting fact is that adversarial AIs doesn't break the systems, it breaks the perception of the system. Small, carefully calculated changes, some print patterns or stickers or noise injections or modified visuals, they look harmless, but they distort AI's classification, confidence completely. Humans see the truth, AI then becomes blind. What I mean is that in the next slide, I want to show you the game or spoofing demo that we have created, especially for the adversarial AI. This isn't theory, this is small interactive simulation we built for the research purposes and want to share with you. So in this game, you are looking at what an AI sees when it tries to classify objects at the sea. So here's in the middle, we have a naval vessel. On the right side, the AI tries to classify what it thinks as is an object. Right now, the system is working normally. It recognizes the ship correctly and systems integrate its eye. So when I take this patch, adversarial patch, it's not a malware, it's not a hacking the computer, it's just visual pattern to design the confuse the AI model. The humans, we still see their ship, but the AI will not. So if we apply this patch into the model, watch what happens when we place it under the vessel. Now the AI starts hallucinating. If you see that when I move the patch, it will be continue to find the misclassification objects as different, like iceberg, oil rig, or cloud formation, or something else. So in other words, the ship disappears from tracking. This is why we called adversarial layer. So for autonomous systems, perception is everything. If the AI can be tricked into seeing something else, navigation, collision avoidance, surveillance, everything becomes unreliable. So this is why maritime cybersecurity today is no longer only about the firewalls or passwords. We have also think about that. Sensor security, adversarial AI, model robustness, human oversight. So the main lesson here is simple. AI helps the ship, but if you don't secure them, it can mislead them. So if we continue the adversarial AI cases, we are not talking about just like ransomware attacks, but we are talking about that specifically exploit how AI learns and makes decisions. So Microsoft has been categorized these AI attacks into classes. So the class one is the model inversion, the first attack. Here, an attacker tries to reconstruct sensitive information that the model has learned. For example, by probing the AI repeatedly, they can extract patterns that were supposed to stay hidden. Class 2 is the perturbation attack. This is the attack type that actually I showed you on the small application demo. Class 3 is the membership interface. In this case, the attacker tries to figure out whether specific data was used to train the model. So very important, train the model that can reveal operational information, routes, behaviors, and other details that should remain confidential. Class 4 is the model stealing. By continuously querying the system, the attackers can essentially clone the model. Once they have a copy, they can analyze it or reverse engineer weaknesses or design more targeted attacks. Adversarial examples in physical world as class 5. This is where the things become very relevant to the ship. So manipulated objects or signals in the real environment, like modified markings or spoofed signals or misleading reflectors, they can cause the AI to see something different from basically reality. If you can see the picture that here on the left, everything works normal, that the AI can recognize the bot as a bot. But on the right side, there you can see that after the adversarial image, that is actually the bot is not detectable anymore, but everything around them is detectable as something false, which lead to some collision probably. So on the previous slide, we looked at how attackers can manipulate AI behavior from the outside. Here we have more deeper into attacks that target the ecosystem around the model. So class 6 for the machine learning models, malicious machine learning provider recovering training data. If you outsource the training to a third party, a dishonest provider may extract or copy parts of your training data for autonomous ships that could expose routes, sensor logs, or operational behavior. Class 7 is attacking the machine learning supply chain. So most AI systems depend on open source libraries, pre-trained models, or third-party components. If any of those are compromised, the vulnerability travels directly into the autonomous ships, basically. Class 8, backdoor machine learning. Here an attacker intentionally plants a hidden trigger during training. So the model works normally most of the time, but when the trigger appears, it produces the attacker's desired output. Class 9 is exploiting software dependencies. Sometimes the weakness isn't the AI at all, it's in the supporting software, frameworks, or drivers, as you know from the general cybersecurity attacks. So compromising those layers can directly or indirectly control the corrupt the model's behavior. Reprogramming the machine learning system instead of attacking the model directly, the attacker forces the system to perform a task it was never designed or validated for, effectively bending into doing something unsafe. Class 11, positioning attacks. So here the attacker inserts malicious data into the training or retraining pipeline. So over the time, the model learns the wrong behavior and nobody notices until it fails in the real world. So when we talk about the adversarial AI in maritime systems, we are not only defending the algorithms, we are defending the data, training pipelines, supplier, and the entire system ecosystem around autonomy. So let's wrap up with a few key points. First, maritime autonomous ship systems technologies are advancing fast, but with that progress comes vulnerability, of course. The more digital, automated, and connected ships become, the larger the attack surface we create. Second, AI is not just a nice extra, it's becoming central to the navigation, decision making, and collision avoidance. If AI fails or it's manipulated, the consequences are optional, financial, and potentially life threatening. Third, the adversarial attacks shows that AI systems can be misled without anyone noticing. So tiny manipulations in data or poisoned training pipelines or compromised components can quickly push the system toward unsafe behaviors. And finally, this brings us to the cybersecurity. Securing autonomous navigation is not only about protecting networks, it's about protecting data integrity, training process, software supply chain, and human oversight. So if you want to master to be safe, trustworthy, and widely adopted, cybersecurity has to be designed in the in the very beginning, not added at the end. So this is what in Emera we are trying to achieve. So we have come to the end of the slides. Thank you again for watching and listening me. My goal here wasn't just to talk about the technology, but to show how autonomy, AI, and cybersecurity are deeply connected and why ignoring one of them makes the whole system fragile. If this topic is actually really interesting to you, whether you are working in maritime, AI, cybersecurity, or the research, I would really like to stay in touch. If you like to discuss the ideas, ask questions, or explore possible collaborations, feel free to reach out. I'm always open to the meaningful conversation, knowledge sharing, and projects that push this field to the forward. So I'll continue posting this content related to autonomous ships, cyber physical systems, and security. So if you want to follow along, stay tuned. Also, in the future, I'm planning to make the video of my published papers. So it will be much more deeply interesting to the researchers in this field. So thanks for your time, and I hope to talk with some of you soon.